Hey guys, this is Miss Miles. This is our second video with Unit 1. Unit 1 is talking about scientific method, life, but it's also an introduction to just science in general. So today we're going to be talking about the metric system. Hopefully, if you're seeing this video, you're already on your Canvas website. So if you will go to Unit 1, scientific method. Um, and click on that. That's probably how you got to this video. So hopefully you're already to this page. So we're working right here today at day 2. This video, once I finish, will be embedded right here at the top of the assignments. And then after this video, you can watch Teacher's Pet metric system video, and that will just hopefully clear up any problems that you're having. But what you need to do right now is go ahead and click on 1.02 metric notes. Your notes for today will be graded. So you'll have to complete your notes as you watch the video. So as you watch the video, just go through and fill in your notes. And then once you're finished, submit that. And then your teacher will grade that as a completion grade for you. So this is what your notes look like on Canvas. You can just scroll through there and see those notes. But I'll go ahead and go to my other site now, and then we'll fill those notes in. So after our notes are complete, we will go ahead and start working on your page that you're going to be completing today for a grade. So I just want to start with the metric system. Measurement systems, think about what we use here in the United States. We use what you'd like to call like the English system. Um, but it's really only used by us and like one other country. So when you're talking about inches or feet or pounds, we use that measuring system, but that's not used by the science world. So typically in science, they're going to use the metric system. The metric system is a little bit easier to use just because it's based on units of 10. So you don't have to remember odd numbers like 12 inches in a foot. You don't have to remember all 4 quarts to a gallon. There's not all of these weird numbers that you have to remember. It's just units of 10. So if you look on the screen there, most countries and all of the scientific community uses the metric system. So it's devised in the 1700s, so it's not a new system by any means. It's an old system. But here in the United States, we just don't use that system. It's based on multiples of 10. So that's a little bit easier, like I said, to convert when you're converting in the metric system. Since it's by units of 10, you're either, dividing by 10 or multiplying by 10. So basically, you're just moving your decimal either to the left or the right. The metric system is also known as the International System of Units. So that is abbreviated SI. So if you ever see anything that says put this in SI units, they're talking about the metric system. It's not IS because in other languages, typically the adjective will follow the noun. So System International is where SI comes from. So if you're following along in your notes, you've written down the words on this page. If you need to catch up at any time, you can always pause the video and then catch up on your notes. So the first measurement we're going to talk about is length. I think you guys understand, of course, what length is. If you're trying to see how long something is or just measuring distance. So it is the distance between 2 points. Length for the metric system, and you'll have to add this to your notes. Typically a meter, centimeter, and a millimeter are the most used metric measurements for length. If you think of a meter, of course, we have a meter stick. That's not a yardstick. So a meter stick and a yardstick are a little bit different. A meter stick is, if you'll typically think about your door in your room or any door in your house or any building, really. A meter is from the very floor to the handle or the doorknob. So that's typically a meter. A centimeter and a millimeter. These are your smaller measurements. Now, I did not put kilometer on there, but a kilometer is also, of course, a metric unit of length. A kilometer is typically used for measuring long distance. So if you're traveling in a car where we might say, I'm traveling so many miles, countries that use the metric system would measure that in kilometers. Centimeters and millimeters are for smaller units. When you're comparing centimeters to inches, a lot of kids will ask, well, how do centimeters and inches compare? There are 2.54 centimeters per inch. So at about 2.5 centimeters per inch. And then a millimeter is a tiny unit of measure. I always tell my kids in class, a millimeter is about the thickness of a dime, whereas a centimeter is 10 dimes stacked on top of each other. So if you can just get that in your brain, that will help you, to figure out how these measurement links relate and how you would use those. Particularly in a lab. Volume is the amount of space an object takes up. When we use something called a graduated cylinder, and here's a graduated cylinder right here. When you use a graduated cylinder, sometimes the liquid at the top ends up being curved. And it depends on if you're using a glass graduated cylinder or if you're using a plastic one. But if you ever use a graduated cylinder and you see that the top of that is curved, that's something that we refer to as the meniscus. So that curvature at the top is very important, because what tends to happen if we read a graduated cylinder incorrectly, it's because of the meniscus or the curvature of that liquid at the top. So the way you correctly read a meniscus, if you'll notice how it's curved here, you have a line going across the top. But if you read from that top line, you're going to get an inaccurate measurement. So the best way to read a meniscus is actually to read from that bottom curvature of that meniscus. And like I said, if you're using a glass graduated cylinder, you'll probably see that meniscus. If you're seeing or using a plastic graduated cylinder, you may not see that meniscus. But we typically use milliliters and liters to measure volume. And you'll remember a liter from things like a 2 liter bottle of Coke or something like that. But milliliters and liters are typically the most widely used form of measurement for volume. Of course, you can also calculate volume by water displacement. If you have an irregular object, you can put that object in water, and it's going to displace a certain amount of water. And then you can take the difference between the beginning volume and the ending volume, and then that will give you the volume of that object. Mass is the measure of the amount of matter in an object. So we would use something like a balance or a scale to measure mass. And typically you would find that measurement useful in grams and kilograms. If we're talking about the mass in you would typically measure that on a scale. And sometimes if you go to the doctor, they might give you your weight or your mass in kilograms, but grams or kilograms is usually the unit of measure that we would use for that. So length, volume, and mass, those are typically the units that we're going to measure. The next one I would like to talk about is density. Density is a derived unit. When you're calculating density, you're talking about how much space an object takes up, but how many particles or how much matter is packed into that space. So something like a lead weight versus a piece of styrofoam, they may take up the same amount of space, but a lead weight is going to have more molecules packed into that area of volume, so it's going to be a lot more dense. If you put a lead weight in water, it's probably going to sink. If you took that same volume of styrofoam, it's going to be a lot less dense. And if you put it in water, it would probably float. So here's the way you calculate density. You're going to take mass and whatever that unit is. typically grams, and then you're going to divide by volume. So that would be a derived unit. So you could write that out. For example, you could say grams per milliliter, and that would be the units that you would use for density. Density is important, especially when we start talking about water. Water has a density of 1. So, whatever units you're using, 1 gram per milliliter would be a good measurement or of density for water. So anything above 1, as far as density, grams per milliliters, that's going to sink in water. Anything below 1 is going to actually float on water. So density is important when we're talking about especially water. And we'll probably come back to that when we get to our unit on water. The next unit of measure is time. Time, if you're measuring time in a lab, you're typically measuring that in seconds. So that would be the SI, or the metric unit of measure would be in seconds for time. So I will go forward. Remember, if you're not caught up, you can pause this at any time and get your notes caught up. Next, we're going to talk about temperature. When we talk about temperature, we tend to think about how hot or cold something is. But really, temperature is measuring the amount of kinetic energy or thermal energy within a substance. So, how fast are those molecules moving? Is it boiling and those molecules are really moving, or is it in a solid form and those molecules are just sitting there vibrating? They're not having a great amount of movement. On your notes, I did add this one. So if you could make sure to add room temperature to your notes. But we're going to talk about the scales. We're going to talk about freezing and boiling, and then room temperature on the different scales. We're used to using Fahrenheit. Every temperature that we give, we always tend to think of Fahrenheit. So to us, Fahrenheit, 32 degrees, if we think of Fahrenheit, then we know that that's freezing. Below that, things are going to be really, really cold. But 32 in the Celsius scale, is pretty warm. So when we're thinking about Fahrenheit and Celsius, we have to really think about that because, in America, we're using Fahrenheit all the time. So if you'll fill in this chart, freezing on the Fahrenheit scale is 32 degrees. Typically, room temperature, we know that to be about 72 degrees in a comfortable room. Some of you might like your room a little bit colder. I know my classroom is always freezing, so it's a lot colder than 72. Boiling, 212 degrees Fahrenheit. So once, water reaches 212, it's going to be able to make that phase change from the liquid state into the gaseous state. And so you'll start seeing that water will start to boil. On Celsius, Celsius is a little bit easier to deal with because, again, units of 10. But we're not used to thinking in terms of Celsius. So, as far as freezing, that's just 0 degrees Celsius. And as far as boiling, that's 100 degrees Celsius. So, when water reaches 100 degrees Celsius, just like when it reaches 212 degrees Fahrenheit, it's going to start making that phase change from liquid to gas. It will start boiling. But room temperature is 23 degrees Celsius. And that's hard for our American Fahrenheit brains to think about. When we think of 23, we automatically think cold. But remember, Celsius scale is much different from the Fahrenheit scale. So 23 degrees Celsius on the Celsius scale would be equivalent to 72 degrees Fahrenheit. And so when we think about that, when we hear 23, we automatically think cold, but it's not. It's room temperature, but it's just on the Celsius scale. So you just have to sort of shift your thinking when you're thinking about temperature there and using the Celsius scale. I did have Kelvin written down here. Kelvin was used to measure like absolute zero. So typically on the Kelvin scale, whatever Celsius temperature you have, you're going to add 273 to that, and that will be the temperature in Kelvin. Kelvin is mentioned sometimes. I put it on here just, in case you do run across that during the course or in your reading. But the Kelvin scale is mentioned right there. Okay, like I said, you can pause this at any time if you need to catch up. We're going to move ahead. So if you'll flip your paper, sorry, you don't actually have a paper. If you'll go on Cami to the next part, you can go ahead and fill in this chart. This chart is very useful for you for converting in the metric system. So in the middle here, I've put the bases. Bases, we have meters, if you're measuring distance. We have liters if you're measuring volume. And then we have grams if you're measuring the mass of something. Now, to the left and to the right, you have prefixes that you can add then to those base unit measures. Over here on the left, we have deca. Deca is abbreviated DA, and it is basically meaning a unit of 10. So, for example, if we have a meter is equal to 1, and then, or it's the base unit of 1. And then a decameter then would be 10 meters. Over here we have hecto. Hecto is equal to 100. So a hectometer would be equal to 100 or 100 meters. And then probably the one that you're most familiar with, the one that you've heard quite frequently, is kilometer or kilometer. So that would be km. As an abbreviation, and that prefix kilo refers to 1,000. So when you're talking about a kilometer, you're talking about 1,000 meters. Going in the other direction, we have smaller units of measure. We have deci, meaning 1/10. I always try to remind people of a decade. A decade is 10 years. So if you can remember decade and deci, deci is 1/10 of a meter if you're talking about a decimeter. So that would be represented by like 0.1. Centi is 1/100th. Think of a century. A century out of the whole scope of time is 100 years. So that's 1/100th. And then we have M for milli. Milli is referring to 1/1000th. If you think of a millennium is 1,000 years. So out of the whole scope of time, 1,000 years. So 1/1000th. So if you look at our chart here, we have decimeter. So it would take 10 decimeters to equal 1 meter. Over here with centimeters, it would take 100 centimeters to equal a meter. And then over here with millimeters, it would take 1,000 millimeters to equal 1 meter. So it may take you a little bit of time to get this chart copied, but like I said, you can pause this video at any time. We focused on meters, but it's the same for liters and grams. Liter would be your base unit. And then, for example, a kiloliter would be equal to 1,000 liters, whereas it would take 1,000 milliliters to equal 1 liter. Same thing with grams. Gram being your base unit, it would take 1,000 grams to equal a kilogram, since a kilogram is a bigger unit of measure. And then it would take 1,000 milligrams to equal 1 gram, since a milligram is a smaller unit of measure. Okay, so once you're finished with that, you're going to use this chart on your problems. So I will probably put a screenshot of this chart on your Canvas, so you can use that to refer to really anytime you would like to. Okay, I'm going to move ahead. If you need to pause that, you can always pause that and finish your notes. So today we have some sample problems. These sample problems, I'm going to work through these with you. So hopefully we'll, come to a better understanding of, what these actually mean. So you'll just have to refer back and forth to your chart, but I will go to your chart too and help you to understand. So on this first one, we are converting 15 kilometers to meters. So the question becomes, how many meters is equal to 15 kilometers? So I'm just going to write 15 right here. Now, if you understand the number 15, I always think of it as in terms of money. If you understand $15, even though the decimal is not written over here, we understand that there is a decimal right here, right after the 5, right after the ones place. So the cool thing with the metric system when you're using it, since it's units of 10, all you have to do when you're dividing by 10 or multiplying by 10, all you're doing is moving your decimal. Now you can go through stoichiometry and have a longer way of doing these problems, and you may have done that in chemistry before, but we're just going to be converting by moving the decimal and understanding that when we're moving the decimal, we're either multiplying by units of 10 or dividing by units of 10. So I'm going to go back to the chart and just show you and use the chart and just show you what we're talking about here. So we're going from kilometers to meters. So what I need to do on my chart, I'm going to start here with kilometers and I'm going to go to meters. So once I go to meters, I'm going to count how many hops it takes to get to my desired measurement. So from kilometers to meters, I'm going to go 1, 2, and now 3, and it took 3 hops to the right. So what that means for you is you're going to take your decimal and you're going to move it 3 places to the right, because that's how many hops it took us to get there. So once I take this decimal, I'm going to pick it up and I'm going to move it 3 places to the right. Well, you say, well, there's nothing over here. Yeah, so we're going to add zeros in the places where we're moving it. Really, this problem just has 2 significant digits, and so we're going to use zeros for the rest of this. So I'm going to take my decimal and I'm going to actually just pick it up and I'm going to move it 1, 2, 3 places. Now, my new decimal location is now going to be here. Now, what do I do in all these empty spaces? I'm going to add zeros. So in all these empty spaces here, I'm going to put zeros. So my new answer is 15,000. Now, when you're writing these problems in, you're going to be using Kami. Um, you can put a comma if you'd like to, but you don't necessarily have to put a comma. But if we were going to put a comma, it would go right there after the 5. But this answer is saying 15,000 meters would be equal to 15 kilometers. So I hope that was helpful. We'll go through pretty quickly and do the rest of these problems. On the next one, I'm calculating centiliters to liters. So I'm going to rewrite over here my 200. Now, understanding that again, my decimal, even though it's not written there, is right after that ones position, right after that last zero. So I'm going to go back to my chart and I'm going to go from centiliters, which is right there, CL, to liters. So going from centiliters to liters, I need to hop 1, 2 to the left. So I'm going to go back here, 2 to the left. I'm going to take my decimal. I'm going to pick it up and move it. 1, 2. This is the new spot for my decimal. So my answer over here is 2, or I could also write 2.00. If you just left a 2 there, that's perfectly acceptable. That is the same answer. 2.00 is really meaning the same thing. On the next problem, on this one, if you look at 4.5, my decimal is already there. So I'm saying that this was 4.5 grams or 4.5 grams, if you would like to think of it that way. So my decimal is already here. So I'm going to pick it up and I'm going to move it. Well, let's look at our chart to see in which direction we're going to move that. So we're going from grams here, and then we're moving to centigrams. So when we go to centigrams, we're going to go 1, 2 to the right. So I'm going to go back and I'm going to move my decimal 2 places to the right. 1, 2. This becomes the new location for my decimal. What do I need to do here in that empty space? I'm going to put a 0. So my new answer is 450. Now, I can put a decimal after that 0, but you don't have to. It's understood to be there. So I can put a decimal there, or I can just leave it as it's written. The next one, centimeters to millimeters. You can look back at your chart, but remember it takes 10 millimeters to equal 1 centimeter. So a millimeter is a smaller unit of measure. A centimeter is a little bit bigger. On this particular one, I'm going to be going from centimeters to millimeters. That's one hop to the right. So I'm going to take my decimal, I'm going to move it one place to the right. Remember, my original decimal is understood to be right there behind that zero. So if I move it one place to the right, I'm going to be adding a zero. So my answer should be, and hopefully you can look at your chart and do this one on your own. But if you're moving one place to the right, your answer should be 200. So there are 200 millimeters in 20 centimeters. The last problem is a pretty big one. We're going all the way across the chart. So I'm going to go back to our chart real quick. I'm going to clear it out. So in this particular chart, let me refresh my brain. We're going from milligrams to kilograms. So I'm going to start right here at milligrams, and I'm going to go all the way over to kilograms. So I'm going to take and I'm going to hop 1, 2, 3, 4, 5, and 6. So I'm hopping 6 places to the left. That's crazy. So when you have a problem like this, so I'm going to redraw my 5,000 right here. Now, understanding that even though I don't see a decimal, my decimal is understood to be right there, right after ones place, right after that final zero. So I'm going to take that decimal and I'm going to pick it up and I'm going to move it. So, and we said how many times we're going to move it? We're going to move it 6 places to the left. So I'm going to move it 1, 2, 3, 4, 5, and 6. Here is the destination for my new decimal. And then remembering in these empty spaces, I'm going to put zeros. So my new answer here is decimal 0, 0, 5. Remember, a kilogram is a big unit of measure. Milligrams are small units of measure. So kilogram being a big unit of measure, this is going to be a small number. If you want to write that correctly, probably another zero needs to go right in front of that decimal. So I hope that that is helpful. That does complete your notes. What I'm going to do now is go back out. I'm going to go to our Canvas here. So your notes should be completed. And remember, as you've completed your notes, you should be able to turn those in. If you ever have a problem turning anything in, I don't see it up here, but you have a turn in button. So you have a turn in button right up here at the top right of your Kami. So you can turn in your Kami assignment right there, and those notes will get checked off for you. So what I'm going to do is go back to Biology 1 at the top. I'm going to go back to our home and then go back to Unit 1. And then once we go back to Unit 1, I'm going to pull up our assignment. So you do have an assignment today, doing metric conversions. So our assignment is right here. It's called 1.03. That's metric conversions. I'm going to click on that. And then this also is a Kami assignment. I think Kami is kind of easy to use. It's easy to write on. But if you look at this assignment here, once it comes up, it's taking a little bit of time. There we go. I think it's coming up. Maybe. Okay. So at the top of this, you have several different things that you're going to be looking at. So on this first one, you're looking at a graduated cylinder. So on the graduated cylinders will vary depending on what type of graduated cylinder it is or how much it's measuring. So it has lines on there. It's graduated with marks. So as we look at a graduated cylinder, we have to determine by what increments those lines are. So that's the first thing you're doing here. The next part on your Kami assignment, the meniscus has been drawn in for you. You are determining how much liquid. So from the bottom of this graduated cylinder to the top, you're determining how much liquid is being measured in that graduated cylinder. The thing that you have to remember when you're looking at a graduated cylinder, if you're in a lab, you have to look at the graduated cylinder, set it on a laptop, get down on eye level to look at it. You can't just hold it up in the air to look at it. but you'll look at that graduated cylinder. If you look at this mark right here on the graduated cylinder, it doesn't exactly make it up to the next level. So on these graduated cylinders, you have to read, remember, by the bottom of the meniscus. And it's talking about the meniscus right up here as well, in the top part of this assignment. So you have to do a good measurement. You have to take the skills you learn in the top part of this assignment, looking at the scale of the cylinder, and then read the measurement there. And I'll help you with a few of those. And then down here, you're going to draw in the line or draw in the meniscus. I've completed the first two for each of these parts. But we're going to go back to our other part here, and I'm going to show you what it's asking for you to do. Let me just skip through some things that we don't need right now. So here we are. This should look very similar to yours, to your assignment. So what I want you to do, we're going to walk through, and the first two are done for you, but I'm going to walk you through those and show you how I came up with those answers. So if you look at this first one, we're talking about this graduated cylinder here, and we can see the numbers 10 and we can see the number 20. Now, we can also look and see how many lines are separating those. So if I look here, I have 1, 2, 3, 4, 5, 6, 7, 8, 9 lines separating those. So if you were to think about 9 lines separating the numbers 10 and 20, that should let you know that you're counting by ones. So if you'll count with me here, I have 10, this next line, 11, 12, 13, 14, 15, 16, 17, 18, 19, and 20. So if you have 9 lines or 9 increments separating two numbers like that, it could be by ones or it could be by 0.1. So you're counting by ones in this case. So that's what it's asking for. It's asking for the increments. So it's already filled in for you on your paper there, but you are counting by one on this first graduated cylinder. Now let's look at this next graduated cylinder. This next one, we have 10 here and we have 20, just like the previous graduated cylinder, but we don't have 9 lines between them, right? So we have 1, 2, 3, 4 lines between them. So let's think about that. What increments could we count by to get from 10 to 20 where we just have 4 increments separating those? So if you count with me, I'm going to go 10, 12, 14, 16, 18, 20. So that lets us know that each of those lines there is going by 2. So we are counting by 2s there. So as you're going through, you're counting by 2s. Now, we're going to get to this part in just a second, but if I were to draw a meniscus right here, notice where the sides are, that's not where we're going to be reading the meniscus. We're going to make sure we're reading the meniscus at the bottom here. So if I were to have a measurement on this particular graduated cylinder, that would be 10, 12, 14 milliliters. 14 milliliters there. So that's not until we get to the next part though. Now your job here is to answer C and to answer D. And I'll just give you a little clue here. This is 1 and 2, right? So it's not 10 and 20. It's 1 and 2, and then we have 4 increments. So I have 1 here. I have 1.2, 1.4, 1.6, 1.8, and then 2. So that should help you to understand that down here we're counting not by 2s this time, but by 0.2. And on this last one over here, I have 1 and I have 2. I have just 1 line separating it. So I think you could figure that one out. We are counting by not a whole number this time. So you need to finish C and D on part 1. Okay, the next one, we'll come back to that previous screen. The next one, we're looking at these graduated cylinders and we're trying to figure out how much liquid is in each one of these graduated cylinders. So this is where you're actually going to have to look at your meniscus. So if we look at this, first of all, we've got to figure out the scale that we're using. So if we look down here, we have a 30 and a 35. So in 4 increments separating it, so we can tell we're going by ones: 30, 31, 32, 33, 34, 35, 36, 37. However, if you'll notice, this meniscus here does not make it up to the 37 mark. Remember, you don't read the meniscus by the side, you read it by the lowest part of the meniscus. So, in fact, right here, this is 36 milliliters. Now, when you're going through, make sure that you also include your units because the number 36, that can mean anything: 36 years, 36 seconds, 36 grams. So, we need to make sure that we mark whatever units of measure we're using. And so this is, since this is volume in a graduated cylinder, that would be milliliters. Okay, going on to part B. If you'll look at B, we have a 5 and we have a 6 and we have 9 increments separating those. So we should know that we're counting by 0.1 here. So this is 5, this is 5.1, 5.2, 5.3, 5.4, 5.5, 5.6, 5.7, 5.8, 5.9. Now, this one is a little bit tricky just because is it right on the line? Is it a little bit below the line? I would say that the meniscus, the sides of the meniscus go up pretty far. I would say that this line didn't exactly make it all the way up to 5.5. So in that case, I would go to 5.4. So listen, you are only as accurate as you read your instruments. So if it doesn't make it to a line, you're going to have to go to the line right below that. Over here on C, this one did make it to the line. So you're right in the middle right there. This one on D did not make it all the way to that halfway line. So you're going to have to look at increments on both C and D and figure out how much is being measured there. Okay, I forgot my milliliters here. So make sure you don't make that same mistake and forget your units of measure. Okay, so the next part is we're drawing in our meniscus. It gets a little bit complicated to draw in a curved line, so I've just drawn a straight line all the way across. So on this one, it's asking you to draw in 49.3. So if you'll look, this is 49 and this is 50. We're separated by 9 increments, so we have 49.1, 49.2, and then 49.3. We're just going to draw straight a line as possible. That wasn't super straight, but we're going to just draw it straight across there. So that would be 49.3 milliliters. On this next one, we have a 10 and we have a 15. We're trying to get to 13. So if you look at these increments here, we have 4 increments. So we know that we're counting by ones. So we have 10, we have 11, we have 12, and we have 13. If we go on up, that's 14, 15. So we're wanting the 13. So on the 13, we're going to draw as straight a line as possible all the way across. Over here on C and D, you'll have to do these two on your own. But no, we have 28, we have 29. We have 4 lines or increments separating those. So we're counting by 0.2s here. So 28, 28.2, 28.4, and 28.6. And that's where you'll need to draw your line. The last one, part D, we're going 60 to 70. We have 9 lines there, so we know we're counting by ones. So we have 60, 61, 62, 63, 64, 65, 66, 67, and then 68. So we'll have to draw our line straight across at 68. Okay, so I'm going to go back to our assignment. So that takes care of the first page. Now, the second page. The second page, most of it's been done for you, but I can go through and show you a couple of these just to get you started. But please use your examples and go by your examples because if your example is right there, if you can work through that one, then you can do the next one. So as you go through, you're just going to use your chart here. Kilogram is equal to kg. Meter is equal to M, so on and so forth. Gram is G. So just use your chart to fill that in. And then on these metric conversion problems, like I said, half of the work's been done for you. So you only have to do this side on this side. I think you can probably work through these. Go back in the video if you're confused, and you can work through those, or you can ask your teacher for help. Um, the last thing that's on here is accuracy and precision. So let me go back to our other chart, and we'll be done in just a second, I promise. But here is your chart. In case you need to refer to that, you can refer to your notes. You can screenshot it, but I will try to put a copy of this chart as a PDF on Canvas so you can pull that up. So accuracy and precision. So what is accuracy and what is precision? So here you have a game, and it's sort of like darts, but it has these foam balls. So the goal every time, of course, we know what the goal is. The goal is to hit the bullseye, right? So you want to hit right in the middle. Um, and you have three different scenarios here. You have figure 1, figure 2, and figure 3. So this person in figure 1, um, they did not hit the bullseye at all. So remember, accuracy is correct. If they were correct, they would have hit the bullseye. So if you look at this figure 1, our accuracy is really, really low. It's non-existent. They have 0% accuracy. And you can explain how you know that because they never hit the target. However, all of their misses, if you'll look here, all of their misses were in the same spot. So if you look at the definition of precision, precision means consistent. So were they consistent in their misses? Yes, they're all in the same spot. So their precision is very high. I would say close to 100% on their precision for sure. And you don't necessarily have to do a percentage on these at all. It just really asks you to explain what their accuracy and precision is in all of these different figures. If you look at figure 2 right here, again, the goal is to hit the bullseye. So if you think about accuracy, they were only correct 1 out of 1, 2, 3, 4, 5, 1/5 of the time. Precision, they are all over the place. So they were not consistent at all. Figure 3, they must have played this game before. These guys are accurate, and you'll need to explain why they're accurate, and they're precise, and you'll need to explain why they're precise. So make sure you refer to these definitions, and those definitions are also on your paper. Okay, so I'm going to go back to your document. So you'll notice I've already done the first one for you. Accuracy was hitting the target, right? Precision is repeating the results, so being consistent. So figure 1, they had no accuracy, right? None of those balls hit the target. Over here, they had good precision because even though they missed in the same spot every time. So figure 2 and then figure 3, you're just going to have to go through there and explain. Down on 2 and 3, it's talking about a basketball player, and they're trying to do free throws, and it's talking to you about how many times they get it and how many times they miss. So use this information up here that we've already talked about and explain accuracy and precision. Now, when you're in a lab and you're doing measurements, you have to be accurate, right? You have to make sure that you're getting close or right on what that measurement actually is. And you have to be precise. You have to be consistent with it and do that every time. So I hope that that helps you moving forward. Also, there is another video that you're going to watch called Teacher's Pet on metrics. And that's it for me today. Go do some biology. Bye, guys.